Alright everybody, grab your torches and pitchforks. It's time for Solids of Revolution. Wait, that's not what I mean by this. Hold on. What I really mean is we have some function, we'll call it like f of x, and what we're going to do is we're going to revolve this function around, in this case, the x-axis, and then that will form a solid. So for example, and these are kind of hard to visualize, so we'll kind of ease ourselves into it, and then we're going to eventually end up finding the volume of these shapes. And so the technique that we're going to use in this video is called the disk method, and this is a well-known way for finding the volume of a solid of, wait for it, revolution. Okay, let's start off with an example so we can see what we're doing. One of the easiest ways to start to visualize what a solid of revolution is, let's say we take a triangle like this, and it's a right triangle, and then what we're going to do is we're going to revolve the triangle. Let's say we cut out a piece of paper and we attach the piece of paper to like a stick, and then what we're going to do is we're going to rotate this stick, and the entire piece of paper will move, and then that will like trace out a three-dimensional area. Can you guess what it'll look like? If you think it's going to look like a cone, you are correct. So if you take this point here, this point is going to revolve around this and eventually end up in the same pace, but the path that it traces out is a circle. And so if we imagine that we're revolving this entire line around, eventually it will revolve around like that, and we'll end up with a three-dimensional shape, in this case a cone. So in this video what we're going to do is we're going to find the volume of this cone. So let's say that it has a length from here to here of 4, so like a height of 4, even though it's lying on its side, and a radius of 2. Well, we know the equation for a volume of a cone, but let's find it using calculus. So what we're going to do is we're going to put an x and y axis on this. So in this case, we are now revolving this cone around the x-axis. And what we're going to do to find the volume is to use something called the disk method. So before, we cut up an area into representative rectangles or representative squares if it was a cross-sectional area. In this case, because it's a revolutionary solid, we're going to cut this into disks. And so follow what I do. What we're going to do is we're going to take this and like cut out a slice of it like this. And so if you can imagine taking a knife and cutting this in half, we're going to cut out a disc shape sort of like that. So we're taking out this red piece, and it's a disc, okay, and it's got like a very thin width. That was a little too thick. Sure, like this. So it's a three-dimensional disc, like a short fat cylinder or whatever. And now we're going to find the volume of this. Well, it's a circle, or it's a cylinder, so the volume is going to be pi r squared, and then times the height. And in this case, the height is the sort of that thickness, and that's going to be our dx. So really, we're just using the volume of a cylinder, where the height is, or the thickness of the small piece is the dx, and then we have to figure out what this radius is. The radius will almost always be determined by the function that you're dealing with. So we need to figure out what the equation for this line up here is. And so if you think about it, well, the slope is going to be 2 divided by 4, which is 1/2, and it starts at the origin. So this equation is simply 1/2 x. And because the radius goes from essentially top function to bottom function here, okay, the radius is just 1/2 x. You can think of it as minus 0, because we're revolving around the x-axis. And so our radius is simply 1/2 x. So let's set up the integral. We're basically almost done once we have this part. Now we just need to integrate from a to b, and in this case a is going to be 0 because that's where the thing starts, and b is going to be 4 because that's the length of how long the cone is going along the x-axis. So let's set up our integral and do it. We have the integral from 0 to 4. This pi is usually brought out front, so oftentimes you'll see answers written with a pi out front. The radius that we had was 1/2 x, and then we have to square that because it's r squared for that circular piece. And then we have our dx. So then when we evaluate this, really it's just a matter of you do have to apply the square to whatever's inside the radius. You can't do a u substitution or anything like that. So we'll have 0 to 4 of 1/4 x squared dx. I'm going to pull this 1/4 out because it's constant. So we'll have 1/4 pi integral from 0 to 4 of x squared dx. The integral of x squared is 1/3 x cubed, so we'll have the 1/4 pi. We'll have a 1/3 x cubed evaluated from 0 to 4. Plugging in 4 and plugging in 0 gives us 1/4 pi, 1/3, and then 4 cubed. The 0 here would go away because you'd plug in 0 and get 0 cubed. So really it's this minus 0, but the 0 goes away. So we have 4 times 3, which is 12, and then 4 cubed is 64. So 64 divided by 12 will simplify to be 16 pi over 3. And this is the volume of our cone. Now, if we had actually used the formula for the volume of a cone, 1/3 pi r squared h, we could have also just plugged this in, and notice that we do get, in fact, the same answer, because 2 squared is 4, and 4 times 4 is 16, so we get 16 pi over 3. And in fact, this equation here is derived from this idea here, where instead of 2 and 4, you use r and h, and you'll get that formula. So it's kind of nice. So in general, for using the disk method for around the x-axis, you'll have the pi out front, the integral from a to b, and then usually it's just going to be like f of x squared dx, because here you're looking at the idea that the radius of that disk is pi, nope, I just wrote pi. It's going to be pi r squared h, and then you're going to integrate that. So that's your volume equation. Go have fun.